welcome back. So what we're going to do today is just do a quick review of everything we've done in the last few lectures and set the stage for what is next. What have we done in the last few lectures? We've essentially solved n simultaneous equations and n unknowns. Now we've done it a couple of different ways. We've done the algebraic way and the geometric way and the linear algebraic way, but it's basically solving simultaneous equations where, this is the important part, the number of unknowns and the number of constraints are exactly the same. So let me first just review that, and then we are going to start to generalize this problem to the condition when you have more constraints than you have unknowns, which in data science is almost always the case. So it's a particularly important way to think about solving linear equations. All right, so let me just remind you where we have been, and then I'll set the stage for what's next. Okay, so classic problem that we've been worrying about. I want to fit a line where I have a slope and an intercept, 2 degrees of freedom, to these 2 points, 1, 2, 4, 5. 2 constraints, 2 points, 2 unknowns, slope and intercept. So what is the intercept right there, and what is the slope of the line? So how did we do that? Okay, let's do it the algebraic way. We start with the model. What's the equation of the model, which is a line? M slope, B intercept, Y of course is this axis, X is this axis here. What do I know? I know that 2, that's the Y component of this point, Y component, is equal to X, which is 1, times the slope, plus the intercept. So I plug in what I know, Y and X, and then what's left is what I don't know. So I know that. So 2 is equal to MB, 1 constraint in 2 unknowns. I also know that 5, which is the Y component of this point, is equal to 4, the X component of that point, times N plus B. I have 2 constraints in 2 unknowns, M and B. And all I've done is I've just taken the 2 points, I've plugged in the X, Y values here, and now I can solve in the classic algebraic way. And let's just go through it since we're here anyway. I'm going to take this equation and I'm going to solve for B. So B is equal to 2 minus M. Now, I still don't know what B is because it's in terms of M, but I now can use this in the other equation to isolate the M. So now let's take this equation, 5. It's equal to 4M plus B. But we just determined from this equation that B is equal to 2 minus M. And of course, I can interchange these because this is the same in MB in both of these equations because I'm looking for 2 unknowns, slope and intercept, that satisfy both of these points. So now I have something interesting here. I have 1 equation and 1 unknown. Well, let's just go ahead and solve it. So I can bring the 2 over, and I've got 3m on this side and 3 on this side. So 3m is equal to 3, m is equal to 1. Now I know the slope. Now I can back substitute it into either of these equations. So here, if m is equal to 1, then b must be equal to 1 to satisfy that condition. And same thing here. If m is equal to 1, b must equal to 1 to satisfy that condition. And now I know the intercept is 1 and the slope is 1. All right, we've done this over and over again. Now let's do it in the vector matrix linear algebraic form. Okay, so let me suggest the following. Pause the video here for me, please, and do the following. Take this problem that we just solved algebraically, and please set up for me the vector solution. So vector times a scalar value plus vector times a scalar value should be a vector. And then please set it up as a 2 by 2 matrix times a vector is equal to a vector. And go ahead and pause the video now. Do that on a piece of paper. Start the video, and then I'm going to go through the solution. All right, I hope you did that, and I hope you got the solution. So let's go through it. Okay, so let's see what we have here. Well, first things first, we know that these unknowns that are scaling the matrices have to be M. So remember, we're going to look at M and B rather. We're going to look at the columns associated with these constraints. This M is common to both constraints. This B is common to both constraints. So that is what I'm going to be multiplying here. Okay, now here, what do I have? Well, let's see. Well, let's do over here, actually. This might be a little bit easier. We know that has to be 2 and 5. That's the right-hand side of the equation. Has nothing to do with M and B. So we should be able to fill that in. Oh, darn, I got the wrong ones. Okay, let's do this one. So this column is 1 and 4 is multiplying M. All right, let's guess what's going to happen here. Well, let's not guess. Let's figure it out. 1 hits B and 1 hits B, so that must be 1, 1. And then, of course, the 2, 5 over there must be what's on this equation. Of course, I've just flipped this to put the unknowns on this side and the knowns on this side. Okay, now once we have that, we just want to bundle this up into a little matrix times a vector, and that's going to be nice because then we can invert this matrix and we can solve for the unknowns. Well, okay, so we know what this is going to be. This has to be 2, 5, and this is still the unknowns. It's going to be something times m and b, something times m and b. So we know we're going to pack in m and b into that, and then what do we pack here? Well, we know that 1 has to multiply m and 1 has to multiply b to get us 2. So that's going to have to be 1, 1, and then 4 is going to have to multiply m, 1 is going to have to multiply b to equal 5, so that must be 4, 1. Or you can think about it as this component multiplies that column of the matrix, this component multiplies that column of the matrix. Well, what's this column? 1, 4. What's the second column? 1, 1. And of course the third column is just 2, 5. So 2, 5 goes over there, and then we get the 1, 1 that I just promised for you, and the 4, 1 here. Or you can think about it, again, in terms of the rows. 1, 1, and 2 is 1, 1, 2. Or you can think about it in the columns this way and this way. Obviously, those are exactly the same. Okay, good. So at that point, we now have this nice linear algebraic framework for specifying linear equations with the same number of knowns and unknowns. And by the way, where do the same number of equations and unknowns come from? That little matrix is square. And once it's square, I can invert it. We just have to invert a matrix, left multiply, and we have our answer. So whether I have 3 equations and 3 unknowns or 4 equations and 4 unknowns, doesn't matter. 1,000 equations and 1,000 unknowns, same thing. Pack in the unknowns, pack in the rows of the matrix, you got a column vector on the right, invert that matrix, done. Now, that always assumes that you have the same number of constraints as unknowns. What happens if you have more data points? What happens if you're fitting a line to a bunch of data points from the stock market or temperatures over time? It's pretty rare that you have exactly the same number of points as you do degrees of freedom in the model. So what happens when you have more? Do you just like throw a bunch of data away? It doesn't seem like it's a very good idea. How do we think about that? That's what's going to come next, and probably one of the most important things for understanding and really basic data analytics. So we'll pick it up in a few minutes when we come back.